Hello, hello. This video will be going over Algebra 1, Semester B, Unit 7, Quadratic Relationships. This quadratic relationships tutorial will be going over quadratic functions, uh, what that relationship looks like, and what that relationship looks like when we try to graph it. So without further ado, let's get into it. So we start our lesson on page 5 with a warm-up question. The question tells us to select all the graphs showing relations that are also functions. So in order to answer this question, first we need to refresh ourselves on what a function is. So a function is a relation, and of course relations just being is a set of two numbers. So when we're talking about graphing a point or graphing a line, that's a set of two numbers. So that is a relation. And a function is a relation that has, for every one input, you have one output. Or, in other words, because we generally refer to our x as our input, for every one x value, there's only one y value. So let's take that definition of a function and relate it to our graphs that we were given. So looking at our first graph, it seems as though this is not going to be a function. And we could test that by choosing any point x and seeing how many y values are at that given point. So if I have x is equal to 2, then I get two y values, that being this one here and this one here. So for my x is equal to 2, I have two outputs. I have two y values. So this is not going to be a function. As for here, this is not a line graph or anything connected. This is just a series of scattered points. So for this one, I just need to check at every point for x and make sure that there are not more than one y value for every given x value. And it seems that we are good. So I'm going to go ahead and select that one. Here, at 2, we have two y values. We have two outputs, that being, of course, here and here. So this one is not going to be a function. Uh, for graph D, if you look at all the x values, there seems to be only one y for each of those given x's. So visually, it looks like you that it is going to be a function, and you can actually confirm whether a graph or relation is a function by using what's called the vertical line test. And that if you take a vertical line and put it through, you know, if you were doing this not on a computer but in person, if you would take a vertical line, a ruler, your hand, your phone, whatever, and drag it across the graph, if your that vertical line hits two y values at any point on the graph, then it fails the vertical line test. But here, I could drag my line across the entirety of the graph and not hit two y values with that given line at any given time. So this one should also be a valid function. This passes the vertical line test at any one line at any given point. There's only one y value for every x value. Here is the exact opposite. There's only one x value given, but there are a bunch of y values. There are an infinite amount of y values seemingly. So this one is not going to be a function. So let's go ahead and check our answer. And that seems to be Correct. On page 8, we get introduced to what a quadratic graph looks like. So the graph of quadratic function is a parabola. A parabola in math is a fancy word for saying that it's going to be U-shaped. Now, this is the standard form of a quadratic, but as we should be familiar with our graphing of linear equations, there are definitely many variations. So, depending on your equation or your setup, you could have multiple parabolas going in multiple directions. There's even some really annoying questions where you get something akin to this going in a diagonal direction. But we won't be covering those advanced situations in this tutorial. So, this is a new graph, so let's go ahead and explore what the domain and range of this kind of graph is. So, again, a refresher, our domain is all possible inputs, but for our purposes, we're going to call it all possible x's. And the implication of this line is that it goes on continuously forever in both directions. So we could assume that this trend continues forever. So the domain for this kind of graph, for this parabola, is going to be negative infinity to infinity. Or in other words, all x's are part of the domain. There's no limit until what x can be here. So that's for the domain. As far as the range, again being all possible outputs or all possible y's, this does have a limit. In this case, the the valley, the minimum of this graph seems to be at -3. And then it goes up, it increases infinitely. So the range here will be from -3 to infinity. Now, this is definitely not going to be the case every time. -3 is just for this situation. But what this points out is that this parabola and all parabolas will have some limit as far as where they peak or where the minimum. So if it were this case, the y would have a maximum of -5 because it starts at -5 and then continues downward. So the domain should be all possible x's, all possible inputs, -infinity to infinity. The range will be dependent on where you start, excuse me, where the peak or where the valley is of the parabola. And of course, once you get into more advanced parabolas, that gets changed on its head, but you will learn to adjust to these types of situations later on in your math career. So on page 8, we start to go over evaluating quadratic functions. So you should be familiar with this terminology, but just in case, I'll go over it. So you should have seen this term evaluating when it comes to expressions or equation. And what it means is that when we have an equation or expression that has variables, it is unresolved. We can't simplify it any further. But we could evaluate these equations if we give some sort of value to these variables. So to evaluate an equation, or in this case, evaluating quadratic functions, what it means is to plug in values for the variables and then solve. And just a slight refresher that this notation denotes a function. This is a function notation, and it is read as function of x. or more often than not, you're going to hear it referred to as f of x. And what this means is that this is a function that contains the variable x. So let's go ahead and recreate and rewrite the given expression above, or given equation. That being negative x squared plus 3x plus 8. So this is your given function. When you're told to evaluate it, you may be told, okay, evaluate this function at x is equal to 3 or x is equal to 1. So you might be given that notation, but more often than not, you'll be told to evaluate f of x at some number, and that number will be given like so. F of, we'll just keep it simple for now, say f of 1. And what this notation means is that whatever your function of x was, for every x value that was in this equation, you now replace it with a 1. So this becomes negative 1 squared plus 3x plus 8. Or excuse me, we're no longer dealing with x. We're plugging in 1 plus 8. So of course that would be negative 1 plus 3 plus 8. So f of 1 would then equal to, what is that? That's 210, apparently. So f of 1 is equal to 10, which means that this function, when x is equal to 1, is equal to 10. And it does give you another example as far as x being equal to 2, x being equal to negative 2. And then, of course, it shows you on the graph what this function will look like. Okay, but moving right along. So let's look at the question on page 14. The question states, the graph of the function g has x-intercepts at x equals negative 1 and x equals 3, and a y-intercept at negative 3. Select the graph that could model this function g. So we're looking for where the quadratic passes through x equals negative 1, x equals 3, and it should also pass through y is equal to negative 3. So let's look at our options. Uh, Option 1 does pass through negative 1 and 3, so it's a contender so far. Our second graph does not pass through negative 1. It passes through negative 3 here. So this one is not going to satisfy our given conditions. Likewise, this one does not pass through a negative 1 or 3 on the x-axis. So we're going to invalidate that one. So our only other option is going to be 4, and we can confirm that it does pass through negative 1 and 3 on the x-axis. So let's see which, if either, pass through y is equal to negative 3. Well, it doesn't do it here. It passes through positive 3, so we can invalidate this one. So this leaves us with this as our final answer, but we can confirm that, yes, indeed, it does pass through y is equal to negative 3 there. So we click that, we submit, and we verify our answer is correct. On page 10, we encounter our next question. It says, consider this graph of a quadratic function. And then it gives us some boxes to fill in. So the shape of the graph is called a parabola. That's just a knowledge check. That is what we call the shape of this graph. So the domain of the function is a set of all real numbers. And that tracks. We went over that it all possible x values are valid for this particular graph. The range, however, depends on our peaks and or valleys. Here, it seems to be a valley. There's a minimum. And where that minimum is that it starts at y is equal to negative 4. And specifically, we could tell that that point is going to be 2, negative 4. But for the purposes of our question, it asks the range of the function is the set of all real numbers greater than or equal to negative 4. And finally, when x is equal to -1, f of x is equal to, well, before on the last page, showed you how to evaluate a function given the equation. But when you're told to find what a function is and you're given the graph, well, you just look at the corresponding x or y value. In this case, we're going to look at x is equal to -1. So we look at our x is -1 here, and we find the point on the graph at x equals -1. This point being -1, that seems to be fine. So when x is -1, f of x is equal to 5. They also could have written this as f of -1 is equal to 5. They could have set it up like that, but both are valid. Submit, and naturally we are correct. So much like other equations that we have explored before, when looking at their graph, it's important to understand the key features and characteristics, or more specifically, the key points for each graph. For linear equations, generally it was the x and y intercept. The slope, though not a point, was an important piece of information. For quadratics, we're going to have very similar points, those being the x-intercept and y-intercept. So here you can see that they've highlighted these points, and this gives you the general shape of the graph. So what you should focus on, or what you should try to learn before you graph your quadratic, is to find out what the x-intercepts are, the y-intercept, there should only be one, and our vertex. This is the peak and or valley that we were talking about before. This is the maximum or minimum of a given parabola. And though, much like a line, it goes on forever, this is where you could, in layman's terms, say that this is the start of the graph, or at least the start of where you're going to graph from. Because the vertex is going to, you're going to start from there, and you're going to form a U on either side. And the neat thing about this is that your graph ends up being symmetrical. So you could graph one side and just mirror the points on the other side. So those are the points you should be looking out for before graphing your quadratic. So we've been given points and graphs, but if you are given an equation, we should know how to graph a quadratic given an equation. And what's going to help us do that is this right here. So we have a quadratic in vertex form, that form being f of x is equal to a times x minus a squared plus k. And this is going to give you all the information you need as far as uh, what your graph is going to look like. So our vertex is going to be at points h and k. So in the example that they give us here, our h, if we look to see what our h is in this case, it's going to be 3. Now notice, it's minus 3 here, but in our vertex form, it's minus h. So if you're given a minus or a negative here, then you make it positive here. However, our k term, which is going to be outside of our parentheses, you see that it's positive here. So when it has a negative sign in the vertex form that you're given, you keep that sign. So our vertex is going to be 3, 4. Once you know it, we go over 3, down 4, there it is. So that's how we find the vertex. And it's called vertex form because the vertex is very easily uh, found when given this form. You may be given quadratics that do not look like this. I think you will very early on when you're learning this, but every quadratic should be able to be written like this. It might just take some manipulation. But that being said, so A is going to functionally act as your slope, but we will go more into detail with that later. For the time being right now, we should just be worrying about being able to identify H and K, uh, planting the vertex, and then, well, I suppose we should go over that. From there, once you have your HK, you have your relevant X term, so you have your relevant input term. So what you should do from there is plug in values that are incrementally one away from that X term. You can go either right or left, but for our purpose, let's go left. So that's going to be 4 and 5, and that should give us a good idea of what our graph is going to look like. So let's plug that in. So that's going to be 4 minus 3 squared minus 4, which is going to be 1 squared is 1, 1 minus 4 is going to be equal to negative 3. So f of 4 is going to be negative 3. F of 5 is going to be 5 minus 3 squared minus 4, which in turn is going to be 2 squared, which is 4 minus 4 is going to equal to 0, so it equals to 0. So we could plot those points here. So that point in turn is going to be 4, negative 3, which is going to be 1, 2, 3, 4, 1, 2, 3. And this point is going to be 5, 0. 1, 2, 3, 4, 5, 0. So if you didn't have this graph already, you could begin to show the shape of what this graph is going to look like. And of course, it's mirrored, so you just plot points opposite the vertex in that same way. If I was a better artist, it would align pretty perfectly. It may go over this in more detail later, but since we're here, I did want to show that to you. So on question 17, it says, use the drawing tool to form the correct answers on the grid. And it says, mark the vertex of the function, then graph the axis of symmetry and mark the point on the graph that is symmetric to negative 3, 0. And then it gives us that equation. So they already set this up for us. We have our vertex of 2, negative 25, which is here. It's our minimum value. It's our valley in colloquial terms. And then what they mean by a line of symmetry, as I said, this graph is symmetrical, which means that it can be cut in half and look like a reflection of itself on either side. So the point of symmetry is going to always go through the vertex, splitting the uh, splitting the parabola into two equal reflected parts. So let's go ahead and put that. We get our mark feature. We're going to go ahead and put that there. Our line of symmetry is going to be like, ooh, not there. Let's undo that. It was one off. Let's just do it here. There we go. So that is our line of symmetry. And finally, we're supposed to find the point that is symmetric to negative 3, 0. So let's find that point. That's going to be negative 3, 0. Okay, so that's 1, 2, 3, 4 away from the line of symmetry, which means that in order to find its symmetric point, we're going to go 1, 2, 3, excuse me, 1, 2, 3, hold on. It's over 1, 2, 3, 4, 5. Okay, that makes sense. I just missed the count the first time. So it's going to be 5 away on this side. 1, 2, 3, 4, 5. So that is going to be the point that is symmetric to negative 3, 0 because it is evenly reflected across the line of symmetry. Let's submit, and we are good to go. So here's a fun fact. When you are given a quadratic, and of course, if we remember from past lessons, a quadratic is a function of the form, or an expression of the form, ax squared plus bx plus c. So we've definitely gone over this a lot. We should be very comfortable with manipulating this, factoring it, and whatnot. But this is actually the same thing as the quadratics we're graphing here. This graph looks like a parabola. And you may have wondered to yourself why we needed to learn how to factor this and spend so much time learning how to factor this. That's because these factors, so those binomials, say you had x minus 3, x plus 5, and you factored some polynomial, you factored some quadratic and got this, this actually tells you your zeros. So we would set this up as you would, the question would be to factor and then solve for x. So you would get x is equal to 3, x is equal to negative 5. Solving for x's and factoring like this tells you what the x-intercepts are for the quadratic. So in this case, we're actually doing the opposite. So that's how this relates. But let me show you how this, we can reverse engineer this in order to get our equation of the line from the graph. So here, it looks like our x's, so our x-intercepts are going to be x is equal to negative 5 and to negative 1, which means that our factored form of our quadratic should be the binomial x plus 5, x plus 1, which then we could multiply this back out, so FOIL it. So that'd be x squared plus x plus 5x plus 5 being x squared plus 6x plus 5. So we reverse engineered this equation, or we reverse engineered, yeah, this equation from this graph by just looking at what the x-intercepts are. So that's definitely a good piece of information to have, a good tool to have in your belt. And yeah, it basically just explains exactly what I went over here. Read through it if you still need a refresher. Okay, starting on page 22, it asks us which two graphs represent the quadratic function with the factors x minus 2 and x plus 3. So that means that there is some quadratic that is of, when factored, has the form of x minus 2 times x plus 3, which means our x-intercept should be 2 and negative 3. Because of course, when we set this equal to 0, we solve for 0, we should get these. If you're unfamiliar with that, please go back and check your quadratics work, your factoring quadratics work. So, which of these have x-intercepts of 2, negative 3? 2, negative 3, so A is a possibility. That is 2 and negative 3, also a possibility. This is negative 2, 3, so not a possibility. We're working with positive 2, negative 3. So once again, no. And this one is just straight up no. So our only two options should be our first two graphs. Let's see if that is correct. I can actually click the button, and we seem to be correct. And it looks like that's it. We end on page 23. The other pages have a summary of what we just went over. If you have any questions, I very much encourage you to look back at this section and look back on this video. And yeah, if you have questions, please throw them in the comments. And I wish you the best of luck on your educational journey. Thank you.